Hello, I'm Natalie Rhea. Today I'll be discussing Lab 5, Magnetic Braking with Faraday's Law for Physics 2212. The objectives of this lab include collecting observational data of a magnet falling through a conductive tube of aluminum foil, most notably the amount of time it takes to fall through the tube, modeling the magnet and tube interaction computationally, and comparing computational predictions with observed data. The important fundamental principles at play in this lab included Faraday's law and Ohm's law, which will be used to calculate the current induced in each ring by the falling magnet, the Biot-Savart law, which will be used to calculate the force exerted on each current-carrying ring by the falling magnet, Newton's second law, to calculate the force exerted on the falling magnet by the whole tube of current-carrying rings, and Newton's third law, to write position and velocity updating code to model the motion of the falling magnet. We conducted an experiment using a tube of aluminum foil and a bar magnet. First, we found and marked the north end of the magnet, and dropped the magnet through a tube of foil. We filmed this with our cell phone to determine how long the magnet spends in the tube. We then repeated this 5 times to determine the average time the magnet spends in the foil tube. We measured and calculated a few key physical properties of the magnet and foil tube that will be used later to create our computational model. The magnetic moment of the magnet, found during our calculations in Lab 3, is 2.87 ampere meters squared. The mass of the magnet is 0.023 kilograms. The length of the tube is 0.305 meters. The width of the foil is 0.005 meters, and the overall radius of the tube is 0.02 meters. After 5 trials of dropping the magnet, we determined that the average time the magnet spends falling through the tube was about 1.14 seconds. Now we create the computational model in GlowScript. First, I initialized necessary constants and created a graph that will display velocity of the magnet versus time. Next, I created a hollow tube to represent the real aluminum foil tube. Then, I created a cylinder to represent the bar magnet, and I initialized the time and velocity values to 0. Next, I defined functions that calculate magnetic field of the bar magnet and the magnetic flux on the foil due to the falling magnet. Next, this loop calculates the gravitational, magnetic, and net forces on the magnet. It updates the magnet's position and velocity as it falls, and calculates the amount of time the magnet is in the tube, and prints the total time. In our model, the magnet falls through a tube, inducing currents as it falls. The graph displays velocity of the magnet in the tube over time, and the model calculates that the magnet is in the tube for 2.763 seconds. The changing magnetic flux due to the falling magnet induces currents in the foil tube both above and below the magnet. The red band represents clockwise current, while the blue band represents counterclockwise current. Flipping the magnet around would reverse the direction of the currents because the magnetic flux would then be changing in the opposite direction. The velocity versus time graph shows that the magnet's speed changes rapidly when it first enters the tube. The velocity remains constant when it is in the middle of the tube, meaning the net force is 0 while the magnet is falling inside the tube, and the magnet reaches a terminal velocity in the tube. The total time in tube of the real-world system is much smaller than the time in the computational model, with 1.14 seconds in real life versus 2.763 seconds in the simulation, at a 142% error. Discussion questions. What if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? Due to Ohm's law, the induced current in the tube would be larger. This means the magnetic force would increase, making the magnet fall even more slowly. 2. What if holes or slots were cut in the tube? How would this affect the ring currents in your model? Resistance in the falling tube would increase, meaning the magnet would fall faster. Conclusion. In this lab, we examined the interaction between a falling magnet and a non-ferrous conducting tube that it falls through. We discussed how the change in flux caused by a falling magnet leads to induced currents in the tube, and we simulated this situation with a computational model. That's all for this lab. Thanks for watching.